Thanks for having me. It's a pleasure to be here. This is actually my first time at Stanford. Somehow, this is the first time. So it's a pleasure to see the campus. I look forward to talking today. So with that, let's talk about control and robotics a little bit. The focus of the talk will be safety critical control. You'll see this message come up time and time again. And before talking, though, I really want to spend 1 minute just thanking my students. Obviously, they're the ones that made this talk really happen, not me. And all the collaborators I have. That's just a partial list. I work with a bunch of amazing people that help bring these ideas together. So with that, I think everyone here that does robots understands or believes that robots are, in fact, hard. They're very hard, right? And you try and try and try again to get something to work. This is an outtake of us trying to get running on in this case, it's a planar robot. So as you can see, it can fall forward and back, but not side to side. And we tried this for 9 months, again and again and again and again, until it just fell apart on us, right? And after 9 months, what happened? 9 months, we got this. We finally got the running, it came together, and it looks beautiful, right? So everybody that does ICRA or whatever knows this is the ICRA video, right? That little segment when everything's just finally going just the way it should. But the lesson here is not so much that we got this final video that worked, that it ran, that everything checked out okay. It's what it took to get it to work. It turns out that the secret sauce, the magic, was not just trying for 9 months to turn a bunch of gains, but actually going back to the drawing board. Coming in and talking to my students and say, listen, we're missing something. I always say nature tells you the right answer. It tells you when you're doing things right. It also tells you when you're doing things wrong. And what we were missing was some math. Turns out that the math we were doing wasn't quite enough. We had to introduce a notion of input to state stability. And once we did that, it worked in like 3 days. After just a couple runs, we got running. So the lesson here is not so much do a bunch of tuning and then get the thing, but rather let's use math to bridge this gap. Let's use math to bridge the gap between what we understand about robotic systems and what we actually see experimentally. And that's really the major underpinning of this talk. That's the major underpinning of my research, is how do we understand this gap? I want to do something where I do some math, where we prove that something will happen. We check it in sim, we put it on hardware, and it works the first time, every time. What will it take to make that happen? So with that being said, I'm going to talk about a bunch of applications of these ideas. As you can imagine, as Marco pointed out, bipedal robots and legged robots are kind of the bread and butter of my lab for a long, long time. They provide great examples of systems where success and failure is this wonderful binary. It either walks or it falls on its face. We're also going to talk about safety critical control, though, on a variety of different robotic systems. And finally, the applications of these ideas to robotic assistive devices. So to me, this is really the place where we can take our knowledge and actually push it to an application domain that can help people ideally restore mobility. So with that being said, I'm going to start with a little bit of math because I'm bound to by law. That's Caltech law, where I have to have at least a couple theorems in my talk. Otherwise, they just eject me from the faculty. And so to begin with, we're going to talk about control Lyapunov functions. So this idea is really simple. People that have taken nonlinear control will find this very, very easy. But if you haven't taken any nonlinear control, I think the ideas themselves are very approachable. So back in 1892, Lyapunov came up with this idea, looking at the energy function associated with mechanical systems. In the 1980s, Sontag took these ideas to control systems, but the idea is really the same. First we have full nonlinear dynamics. We have n-dimensional nonlinear system. I'm going to assume it's an affine form. And for this system, we consider a Lyapunov function, in this case, a Lyapunov function candidate. And the idea is really simple. It's basically a bowl, just like this picture indicates. And if you have a function that looks like a bowl, that goes from Rn to R and has this nice positive definite structure, the main idea is that when you differentiate this function along solutions of the system, its derivative points in the downward direction, if you'd like. Or specifically, the derivative of this function looks like a stable linear system. Then you're necessarily going to have convergence of that function to 0. If that function converges to 0, then your state will converge to 0. Hence, you will stabilize your system. So long story short, certifying the stability of an n-dimensional system amounts to just checking the derivative of this function and making sure it satisfies these properties. So the way I like to think about this is, who's ever seen these fair games, right, where you put a coin in? Right? Okay. So this is actually the Minnesota State Fair where I'm from. I took this video myself. I then made my wife stand in front of this and take pictures with me, and she didn't love that, but she did it. And the idea is this is Lyapunov function in a nutshell, right? As long as things are heading downwards, you know they'll ultimately end up in the bottom. So mathematically, what does this mean? Mathematically, this means if we can find an input to our system, a control input, such that the derivative does the right thing, then any policy that makes the derivative do the right thing, that makes this v decrease, will be guaranteed to exponentially stabilize your system to 0. So once you understand this basic idea that all you need to do is find a function v that satisfies this condition, you can synthesize controllers. Okay? In particular, one way to do this would be as a quadratic program, where now you just say, given my input, find any input that satisfies this subject to any cost I want. It turns out that this is a Lipschitz continuous controller under the right conditions, and in fact has a closed form solution. It's a quadratic program because, as you see up there in the math, the input is affine in this inequality constraint. So we're just checking a quadratic program, which, as you know, is a convex problem which can be solved at the kilohertz level. So this basic mathematical framework gives us a theorem. And the theorem itself is not so important. I want you to just have a block that there's a theorem there. And this theorem says, for example, that we have stable robotic walking. So this is this theorem instantiated on multiple robots. There's a lot of stuff under the hood here. The references are throughout the talk. These were actually the first couple generations of robots I worked on. These were custom built in my lab back in the day. They're a little simple by today's standards, but at the time it was really awesome to see the theorem realized. This is Atreus, built by Jonathan Hurst at OSU. This is actually the precursor to Cassie, which I'll show later. And so this theorem really works. Of course, the one problem with what I just told you is that this theorem works, but the computational instantiation of this theorem is actually really hard. You have to check all these conditions. You have to synthesize this Lyapunov function. So the other important point with all this math that I showed you is the algorithmic side. So with all this math, we have to write it in the end as an algorithm. And so one of my students who's now at Ohio State came up with this Frost toolbox. So what this does is takes all these theorems, all this math, instantiates it in particular, it's a nonlinear constrained optimization problem. We use co-location methods, etc. So in about 5 minutes, we can go from the math to the robot. And this video on the right is the result of this optimization problem put on the robot fairly cleanly, meaning there isn't a lot of hacking happening here. Really, we're taking the trajectories from the optimization problem and popping them on the robot itself. So this is the throughput. We start with this idea of Lyapunov functions. We get to a theorem, we write it as algorithms, and ultimately we realize it on hardware. And once you have that loop, because it's very general, you can start to apply it to a whole bunch of different robotic systems. So another example, this is Duris again, but now this is Duris doing multi-contact walking. So I didn't talk about it, but under the hood of all these things is a hybrid system model. If you know hybrid systems, that means we have 4 different discrete domains for this walking model. We have corresponding Lyapunov functions on all these domains. And the important part here is that first, we're doing this natural heel-toe contact. So we're able to instantiate this human-like walking. The second important point is that Duris, if you didn't notice yet, has springs at its ankles. So it naturally has passive dynamics that we have to leverage to achieve this locomotion. This is one of the most efficient examples of robotic walking ever realized. And the reason is, in my opinion, because we're leveraging the inherent nonlinear dynamics of the system to achieve the walking. So I still love this video. It's a couple years old now, but I still think it's awesome. The other thing to note, of course, is that this was done by 2 graduate students, one being a young in the back, over just a short period of time. So that's the other thing, is we have to deal with less resources than, let's say, Boston Dynamics, but we can do it with the right math. So we can apply this to other domains too, though. Because it's math, it's general. So this is actually a really recent result now, where we take the same ideas, that is, with this method of generating gates in formal controllers for bipedal robots, and apply it to quadrupeds. In the case of a quadruped, we just view the quadruped as 2 bipeds that are connected by reaction forces at the torso. So basically, it's 2 walking robots that are kind of holding hands through the torso, right? And the interesting thing is, because of the quadruped structure, we can generate gates for quadrupeds in about 3 seconds. That's 3 seconds from pressing the go button to realize it in on hardware using the full nonlinear dynamics of the system. That is, there's no reduced order models here. This is just straight full order dynamic models. So this shows, again, the extensibility of the theory to do interesting things. Of course, the great thing about quadrupeds is they're really robust, especially when compared to bipeds. So this is us taking the quadruped on this root system right outside my office at Caltech. You'll actually notice it gets a little airtime right about here. There it goes. So the other thing is, I was actually shooting this video, and after it did this, it turned direction, and we weren't controlling its direction. It just started coming right at me. So I was kind of, for a moment, wondered whether this was the moment that robots take over the world. And then I realized there's no ML on this robot, so I'm probably safe. No, but the point is that we can apply this to a bunch of different domains. So the final bit, of course, in this light is that the same ideas apply to different bipedal robots. So this is Cassie. This is built by Agility Robotics. And the same theorem applies. It doesn't matter that the legs are inverted. It doesn't matter there are springs everywhere. The math is the math. And so what I'm showing first is just that we get a really nice agreement between the sim and reality. The great thing about Cassie is, unlike Duris, is it's meant to go in more natural terrain environments, so we can take it around the lab. We can take it outside on flat ground. We can even take it outside on rough terrain. So this is a single gate that we generated with a single controller doing all of these things and just showing the robustness of it. So there's no hacking to handle the terrain versus this environment versus this environment. So the goal here, again, is to demonstrate that the math is reasonably extensible. Okay? But even with robustness and reasonable extensibility, it has its limits. Before talking about that, here's some jumping because it's fun. There's no other reason. This, again, is the same idea that once we know the math, we can apply it to a bunch of different domains, not just different robots, but different walking types. So that was jumping. This is fast walking now. Same controller, same framework. We're getting about 1 meter per second, which is pretty good, even though, like I mentioned, we're not planning for this walking speed. This is just one controller running all these different behaviors. So this is just for fun. Okay. So one more thing. We're starting, now that we understand walking, we can start to think about doing more complicated autonomous maneuvers. So in this case, we're trying to walk around this square. Of course, a walking robot with legs can't directly track the square, but what we can do is use this framework to actually understand what trajectories are allowable around the square and then correspondingly track the square as close as possible. So I'm just showing that with the math comes this repertoire of different environments that we can approach. And as I mentioned earlier, while we're robust and while that's awesome, I need to show that it has limits, and these are the limits. Same root system I showed earlier on the quadruped, but now for the biped, it doesn't quite make it. It was really close, actually, just about made it through. So it's hard to tell maybe from the video, but these roots are a good 3, 4, 5 inches deep at places. So it's non-trivial. And of course, remember, there's no cameras on this robot. It's not looking at the terrain. It's not percepting. It's not doing foot placement. This is just sheer robustness of the nonlinear controllers to unknown disturbances to the system. So thankfully, the robot was not harmed. It actually got right back up and walked again, which was pretty cool. But this also shows the limits to what we can do in terms of just applying theory without thinking about the environment that we're interacting with. So that leads to the second point of this talk. The second point of this talk is safety critical control. And in some ways, the Lyapunov stuff I talked about earlier was the setup. The Lyapunov methods have been known for a long time. CLF-based QPs are fairly new, and you can do a bunch of cool things with them, but it doesn't get us where we want to be in the safety-critical control context. We don't want to necessarily stabilize every system. What we really do is want to make every system safe. And so the point is we need something more general than Lyapunov. And for this, we're going to introduce control barrier functions. So this is a Lyapunov-like extension to safety. So before doing that, I want to start with a little history, because I think history is really important. Sometimes in academia, we get caught up in just talking about the paper we published 6 months ago, and that's all awesome. But these things go back a long ways. So it turns out this notion of safety that I'm defining here goes back to Nagumo in 1942. What's crazy is Nagumo's theorem here was lost in time at least 2 or 3 individual times. I mean, it was rediscovered independently multiple times. But it traces back to him in 1942. You can imagine this was kind of a bad time for the world, so you could see why things were lost at this moment. So beginning with, we have dynamics. Again, fully nonlinear dynamics. No assumptions, except I'll assume they're affine. We define a safe set. Our safe set, now we can argue about whether this actually defines safety or not, but for these purposes, I'm going to say safety is staying inside a set C. That is, the set is forward invariant. Initial condition in the set means the solution stays in the set for all time. Okay? And in particular, we're going to define our sets as being the super level set of a function h. That is, there's a function h that maps from R into R, for which all of its positive values define the set. So the question is, what does it mean to be safe in this context, that is, stay inside the set? Okay, how do you check that? Of course, we don't have solutions of the system, so we need some sort of derivative-like condition to check it. It turns out Nagumo figured this out a long time ago, 80 years ago. And the answer for when we don't have a controller, that is, we just have dynamics, is actually really simple and intuitive. As long as the derivative of h along solutions, which is just the gradient times your vector field, is positive along the boundary of your set, you're guaranteed that your set is forward invariant. Not only are you guaranteed forward invariance, but it goes the other way, meaning these are necessary and sufficient conditions for safety, that is set invariance. Okay? Now that's really interesting and really fundamental, and the idea is intuitive. If if your set C is defined by H being positive, then if along the boundary H can only grow or stay 0, then H itself has to stay positive, right? So that's clear. That's clear why that might be true. Now, this idea was extended a long time after Nagumo. We're talking 2004, 2007. There's also some of this in Oban's book from the late 90s. But the idea is let's take this notion of safety from Nagumo and let's extend it to the whole set. And now we're going to do this with a control system. So the idea is we had this condition on H dot being positive. Now we have a control input. So if there exists a control input, such as this is true for all points in my set, then my set will be safe, right? And this just follows from Nagumo's theorem. Is everyone convinced by that? Okay, again, as long as this H dot is positive, we can't leave the set. But there's a problem. What's the problem? The problem is this is way too conservative, it turns out. Why? What do I mean by conservative? Because it turns out that if you check this condition on all points in your set, what does it mean? It means every super level set of H is also invariant. That is, I show it graphically there, but if you started with H being greater than some positive constant A, H will always be greater than that positive constant A. So if my safe set was this entire stage, then this says wherever I start, I'm going to stay in a smaller region. That's safety, but that's not what we want from safety, because safety should be I can come all the way to the edge of the stage without falling off, right? So the question becomes, how do we extend Nagumo's theorems to the entire set? And that leads us to 2014, so not that long ago. So I was working with Jesse Grizzle and Paulo Taboada, and we came up with this idea that there must be a nice way of extending it. In particular, and this is the key point, is we need to allow H dot to actually go negative sometimes. Because H dot has to go negative so you can approach the boundary of the set. At the same time, it can't go so negative that you shoot over the boundary of the set, right? As you approach the boundary, it must go to 0. So the idea here is let's take this H dot condition and let's bound it below by minus gamma. This is a class K function for those that know. For those that don't, consider it a constant times H. So when you're inside your set, H is positive, so you're lower bounded by a negative number. So that means H dot can actually go negative and decrease. When you're on the boundary of your set, this becomes 0, and you recover Nagumo's theorem. So it turns out that this, and this is the important point, is this is necessary and sufficient for safety, meaning on the entire set. Meaning if you check any point in your set, if this is satisfied, it's true if and only if you're safe. Okay? And this, by the way, we're now in the digital age, so I was able to find the scrap of paper where we first wrote down this condition, and that's what this is a screenshot of. But this is the idea. So what can we do with this now? So now that I've done the math, we can do something with it, okay? So if everyone believes what I just said, and you're welcome to check it out, there's a lot of math under the surface, then now we understand safety as this simple derivative condition, okay? So what we can do is, just like we did with Lyapunov, check this in a quadratic program, right? In this case, we can take any desired input you have to any desired controller. This could come from a machine learning algorithm. This could come from something you don't know, you don't trust. And we can filter it through this safety critical controller by just picking the U that's closest to the existing U subject to the safety constraint, right? And the end result is, first, we have a nice closed form solution if you want it. So this is easy to solve in real time. And second, we can filter our inputs so that we're safe. So what you see here is a segue. And what we define as safety is a segue staying plus or minus 15 degrees. Okay? So on the top, we have a PD controller. In both cases, we have a PD controller. In the top, my student kicks it, causes a PD controller to overshoot, and the segue falls. On the bottom, we filter the input through the barrier function, and we stay within this set always because of the barrier function. So that's safety in a nutshell. Now, everyone with this? Okay. So, well, what do we do with this? I'm going to show some applications now. We made it through the math part, but I think it's important to understand what these things mean. And with that, one more bit of understanding that I think is very interesting. This is a trivial statement and a trivial proof, but it's actually, I don't want to say this, but somewhat profound. And what I mean is the following. It turns out that the set of all Lyapunov functions sits as a subset of the set of all barrier functions. In particular, Lyapunov functions are a special case of barrier functions when your set is a point. Because not only do barrier functions keep you in the set, but they actually stabilize you to the set outside of the set. And that's a proof of this right here. So the point is we haven't lost anything by going to barriers. We recover Lyapunov as a special case, but we've gained something because inside these safe sets we can move around freely, but we know we won't leave the sets. Okay? So with that, let's see this stuff in action. One of the cool examples of this came up when I was at Georgia Tech with Magnus Egerstad. So he, if you don't know, is a multi-robot system guru. And we had this idea that at the time of the Robotarium, he had the idea of the Robotarium, I should say, and I was at Georgia Tech, so I'm like, that's great. But so the Robotarium, the idea with the Robotarium was we're going to have this multi-robot testbed, and people from around the world can implement their code on this testbed. And it's still going to this day. You should try it. It's actually really cool. But the point is that what is the first thing people will do when they put their code on robots? What are they going to try to do, I should say? Crash the robots, right? That's what I would do. Let's see if we can crash the robots. So the idea is let's use barrier functions as a safety filter, as a safety layer on the Robotarium to prevent the robots from crashing. But this is the other important point. We want to do it in a minimally evasive way. That is, we want them to implement their algorithms. And if their algorithms are right, we don't want to do anything. But if they're wrong, we want to keep it safe. So here's an example. In this case, imagine the user to the Robotarium implements an algorithm where we want this robot to go straight. Of course, if all the robots go straight across the circle, they're all going to run into each other right in the middle, right? So then we filter it with a barrier function that's a safe region around the robots. And you see they're coming in, it's looking bad, and then there goes the barrier. So when they get in, the barrier takes over, and it's like these little virtual force fields around all these robots, and then they end up spinning. The interesting thing here, of course, is that there's no planning happening here. This is not a centralized decision-making process that they should start to spin in some direction. Rather, the barriers just cause them to roll off each other until they finally get free of each other and can go to their ultimate destination. So just to show you it's true for different types of robots, this is the same idea, except now we have a human controlling a drone, specifically a grad student, and these 4 drones are all on autopilot, quote unquote. And what he's going to do is try to crash one drone into the other drones. So this is what's happening. And the only thing preventing them from hitting each other is the barrier function under the surface. And I should note that this is done on the full nonlinear dynamics of the system. Turns out differential flatness gives you a nice way to synthesize these barriers, even for the full nonlinear dynamics of the drones. And so you can see that nonlinear dynamic behavior with all these oscillations. Okay, so a couple more examples just to show it's not limited to multi-robot systems. This is actually a video done by my postdoc, who never actually published a paper on it, but this is an automotive application with lane keeping. So in particular, here you have a lane. Barrier function defines the lane. And this controller is keeping the car in the lane despite what the human's doing. So you desire it as a human. So you can see here, on the left is the control going to the car, on the right is the human. And you'll see these steering wheels don't align all the time because the human's trying to drive the car out of the lane, and the barrier function's taking over when you get near the boundary of the lane and keeping the car in the lane, right? So this is a safety feature application. There's a lot of applications in the automotive industry in this context. One more application that's kind of interesting is Yamaha. We've been working together a little bit, especially with my students, and they want to implement safe features on boats. So it turns out this works on boats too. In this case, the barrier function is don't hit the dock. The human is driving the boat and trying to ram the boat into the dock, and the barrier function takes over and prevents the boat from doing it. And the reason I'm showing all these videos is they're all examples of very different dynamical systems that are being kept safe in this context. So with all that being said, a little bit of recent research that I think is important and interesting is everything here assumed that we had a model of the system and that model was correct, right? This is a model-based derivative. So the question becomes, what about the real world? What if we don't have perfect models of the system? So in this context, it ties into learning. So the idea here is don't learn the whole dynamics, don't necessarily filter a learning input, but rather let's take the real world instantiation of the system and learn the deficits as they relate to the barrier function so we can enforce safety even if we don't have perfect models. So a little more concretely, this is the process, and it's a very simple, straightforward application of learning. The non-trivial part is applying it to the barrier function specifically. So what we do is we do empirical risk minimization, as you would imagine. And in this case, what we're doing is we're looking at sort of the difference between what H dot we would predict we would get from the model versus the H dot we're actually observing from the system itself. And the goal is to make those as close as possible. That is, learn this remainder term in the H dot derivative such that everything lines up perfectly, right? Once we learn this, we hopefully can guarantee safety. We do this through an episodic learning approach. And this is what it looks like on actual hardware. So this is the other important point. This actually really works on hardware. This was a demonstration done about a month ago. So on the top, we have with and without learning. So without learning, what happens? When you're driving the Segway, because there's uncertainty in the model, you're going to go unsafe. You leave the safe region. The learning means that we've learned these deficit dynamics, and hence we can keep the system safe even with this uncertainty in the system. So these are the kind of applications we're looking at in the learning plus control domain, is take our models, take our mathematical understanding of the system, and then apply it to these very dynamic nonlinear systems. So one final note is some other recent work we're doing is on the MPC front. And I think this is important to note for a couple reasons. First, these CLFQPs and the barrier functions that I showed you are not MPC. They're different in multiple respects. They're the same in that you're solving an optimization problem, a QP. The difference is these work for the full nonlinear dynamics of the system as is, no linearization needed. MPC, if you know, works for the linearized dynamics or a linear system. The question is, can we bring these two together? So the advantage to the MPC is that it lets you look out over a longer time window. The CLFQP, you can only look instantaneously. So the question is, can we take that time window and add CLF constraints to the longer time window to get better performance? So we're starting to try to understand that interplay. And we're doing this on hardware because that's where it really matters. So again, back to the Segway, we're starting to play with all these different instantiations of CLFQPs, MPC, and the combination thereof. And the hope is to understand the best way to do optimization-based control online on these dynamic robots. And the ultimate goal, of course, is to handle uncertainty in every possible way. So this is a recent video about a week ago now, actually. And here we inject uncertainty at all levels. So we have uncertainty in state estimation. So that means the Segway doesn't really know where it is. We have uncertainties in the model. All these uncertainties add up. And what we want to do is guarantee safety. In this case, safety is staying within this region and staying upright, doing all those things at the same time. And if we properly model and handle the uncertainty, we can stay safe even when this system up there clearly doesn't, right? So that's where we're heading on the safety side. Right? And bringing safety into the system. Okay, so now that we've done Lyapunov and we've done safety, we showed these examples on multiple robot systems. We've covered a lot of ground already in a short period of time. There's one more layer I want to talk about, one more important piece of the robotics world that we need to focus on. So everything we've done so far has been on the low-level control, right? If you're a control theorist, this is your natural domain, right? We have dynamics, and we do things like avoid things, we stabilize things relative to a plant. The question becomes now, how do we bring in other levels of decision making, for example? And so this ties now into autonomy. So to achieve autonomy on systems, what do you need to do? You need to think not just about the low-level continuous domain, but also this discrete level decision-making domain. Okay, so how do we bring these layers together? So if you're a roboticist, you know typically these things are done in a highly decoupled way. The control theorists come in and it stabilizes the system. Once they have a stable system, they give it to the computer scientist. The computer scientist does a bunch of planning with that and gets it to do more macro-level behaviors. So can we bring these two ideas together? And let me start with a little motivation for doing this on the Markov decision process level. So we started thinking about this actually relatively recently in the context of the Mars 2020 mission. So for this mission, you're going to have a rover and a helicopter. The helicopter will have about 2 minutes of flight time. The rover obviously can go basically all day on a charge. So the question is, how do you coordinate these different robotic systems? But it's not just a coordination problem because there's a safety component. Obviously, you don't want the helicopter to crash. There's also an information planning and passing component because the helicopter will have a lot more information at the macro level than the rover does at this sort of local level. So how do we take and combine all these things together? So we worked on this in the context of Markov decision processes. So this is an experimental demonstration of what we did. So we have a rover, in this case a Segway, and this is the helicopter, a drone. This is a completely autonomous demonstration, meaning my students hit go and then nothing else. So what's happening here is they're each utilizing their own capabilities in the context of a Markov decision process to build a better image or better representation of the world. So the rover went out, it couldn't find the sample, so the helicopter mapped the environment, passed that information back to the MDP associated with the rover. Then the rover knows where to go and ultimately can get there with high probability. So the idea is to bring these two pieces together on the planning side. Now, what did I ignore in this whole process? Safety. So I just spent all this time talking about nonlinear dynamics, nonlinear control, all these wonderful things, yet I didn't talk about safety in this demonstration at all. So it turns out that even though that was completely autonomous and my students hit the button and then it went, that was autonomous the 100th time they hit the button, right? Every previous time, it did things like this. So you can't actually see. I was recording this, and then I freaked out because the drone started going like this. There's a time delay that propagated through the system and ended up flying into a wall and breaking into a million pieces. It turns out that happens so often that my students rebuilt the drone so that it would hit a wall and break apart, and then they could reassemble it right there to run another experiment. So you know you're not very robust if you plan on the thing breaking apart into a million pieces so you can rebuild it, right? They still did great. I'm not downing my students, but I'm telling you sort of the need for safety critical behavior. Other couple examples, the drone thing I showed earlier. When time delays propagated through the motion capture, they would collide, right? Even though we're provably safe. Again, provably safe is provably safe subject to the assumptions you're making on the system, right? Of course, you've seen the Segway fall multiple times. So this leads to our final component at the technical level, which is doing safe autonomy. So here we're going to do safety critical POM-DPs to understand this at a better level, and you'll see how this all connects back up with what I talked about earlier. So in particular, we're going to use control barrier functions. So for these POM-DPs, we have these sort of probabilities that tell you where you're going to go at any given time, given some discrete structure on the system. And the interesting thing is that you can write these POM-DPs as discrete time dynamical systems that update these sort of probabilities. Turns out this actually goes back to some work by Max Schwager in 2013, where they had these kind of formulas for the evolution of the system. My postdoc did this work as well. And the important point is you can understand this discrete system and its evolution at a probability level through this discrete time dynamical system, and we can start to reason about this discrete time dynamical system now and safety thereof. In particular, we can define barrier functions for discrete time dynamical systems. This was also done by Kaushal for the just normal discrete time case, Kaushal Srinath at Berkeley. But it's exactly what you would expect. This is a discrete time sort of derivative subject to a class K function in your function. The point is we have barrier functions for this discrete evolution of the system. Once we have these, we can prove that in fact these are necessary and sufficient for safety, just as I talked about earlier. But now, again, remember, we're dealing at this discrete level, this probability level for the system evolution. And that means that for this level, you can make sure your robots, for example, don't hit objects in the environment, because that's what safety means at that planning level, right? You can also do more interesting things. And this is where things get really interesting, because you can start to think about doing things like having multiple sets where you intersect them and you union them. And so what you're doing now is instantiating specifications. The specifications might be always stay within a collection of sets, right? Then you're doing an intersection, or stay within the union of sets. And for these different behaviors, you can write this as barrier function conditions on the POM-DP, or the discrete time dynamical system associated with the POM-DP. This leads to the final point, which is you can actually instantiate a whole bunch of specifications. So this is a bunch of temporal logic specifications. And I just highlighted the two I showed you earlier. There's a whole bunch of other specifications you could do at this high decision-making level. That is, you can formally verify that your system satisfies these specifications and check it through barrier functions. Then you can also do what I showed you earlier, which is filter any given policy through the barrier function to find the policy that actually meets your specifications, even if your original policy didn't. So the lesson here is we've gone from continuous level dynamics, where I took a control policy and I filtered it, I modified it to guarantee safety. And now we're at the discrete planning level, where we can also filter a policy so that we guarantee safety. So we can do this at multiple tiers and multiple levels of the system. And in this context, we're looking to realize this on multi-robot systems, specifically heterogeneous multi-robot systems. So now each of these systems might have their own barrier functions on them. For example, at the continuous level, the Segway does. But then they're going to, at the discrete level, use this POM-DP representation to coordinate to try to find a sample In this case, it's the Christmas present. This was filmed in December, so Christmas present. So what happens is each of these robots have their own PalmDPs that's interacting through some sort of macro level PalmDPs. So information and probabilities are being passed between all of these robots. And first, the most capable locomotion robot goes out, then the next capable robot. And in the end, they've mapped the environment with reasonably high probability. They know where the obstacles are, and hence they can send the final, in this case the rover, to actually go retrieve the sample. So you're bringing through autonomy at multiple layers. So we hope to actually extend this even further, because what I did so far was sort of a compositional safety at discrete level planning. You could also imagine an interaction level of safety, right? So this is actually a movie that my students took. We were getting ready for a lab tour, and I walked into the lab and they were just doing this. So this is what my students just do sometimes when they're waiting for lab tours. And so they're controlling these robots. This is not autonomous. They're using joysticks. But they like to kind of see how close they can get the robots, which terrifies me, to be honest. I'm just like cringe. And they do this cool stuff where they're clearly sort of passing information, right, by doing this. So the question is, how do we add this to this discrete level planning where we guarantee safety? This is not guaranteed safe. That's why it freaks me out. But also we can use coordination and collaboration between robots, even at a dynamic level, to make decision making and do interesting things. So that's where we want to head. All right, so we've taken through the math, we've taken through the theory. Let's get to the final piece in the remaining minutes, what I think is really exciting. So no more heavy math, we're done with that. You've now graduated to the reward at the end of the rainbow, which is getting to things like robotic assistive devices. That is, what are the applications of these ideas? And I think robot assistance is one really wonderful application where we can actually make a real impact in people's lives. So starting with, this is the video I showed earlier of humanoid robot walking. Now, once we make robots walk and understand how they walk at a mathematical level, what does that imply? We can hopefully help people walk better, right? That's a very straightforward thing, but it turns out it's not quite so simple from a mathematical level. But this is essentially what we're doing in my lab right now. So first, this is a prosthetic. This is the 3rd-gen prosthetic we've built from scratch in my lab. And this prosthetic is running a quadratic program in real time as the controller based on control Lyapunov functions. So we're able to translate the math and the nonlinear controllers to the device. And then also, we generate gaits for the prosthetic as if it was a humanoid robot. That is, we take the human, we generate a model of the human, a model of the prosthetic, and we generate formally stable gaits that we put on the device itself. So we're able to make that transition from robot walking to prosthetic and actually have it work in the real world. What I mean is these are 2 of my graduate students walking outside with the device showing their robustness. So that's one application. Now, the one thing about prosthetics, I love prosthetics. It's a really wonderful and compelling application. But humans are very robust at making prosthetics walk, right? You don't really know how much is the prosthetic or the human in this case, since they can walk with a peg leg, right? So that leads to the second application that's I find incredibly compelling, which is exoskeletons. So this started a couple years ago. This is joint work with Jesse Grizzle at Michigan and Kaushal Srinath at Berkeley. And the idea was if we know how to make robots walk, we can put that on exoskeletons that hold humans, make them walk dynamically, hence make people walk dynamically even if they can't walk on their own, right? And so it turns out this theorem I was showing through the whole talk, it's from a 2014 TAC paper, and it's this theorem represented as algorithm that's living on this device that I'm just about to show you. So it was about 4 years from TAC to device. Now, where this is joint work, I should say, a lot of joint work, meaning all the mechanical design and algorithms were done by Wondercraft, a startup company in Paris, France. And this is the device walking stably, dynamically, with the math under the surface. So you see the stable periodic orbit. Now, the important thing is once the device can walk, somebody can get in the device and walk with it. This is a complete paraplegic. He has absolutely no function of his legs whatsoever and hasn't for 10 years. And this is, as far as we know, the first example of paraplegics ever walking without crutches with an exoskeleton. That is, walking dynamically with an exoskeleton. And these are 3 examples, and there's been over 20 people that have now walked clinically with this exoskeleton technology in Europe. So this, to me, is the ultimate application of an idea where you can prove some math, do some, that's all wonderful, but in the end, this had a real impact on their lives. So it's very powerful, and hence we want to take it further. We want to build on that success. So we just started what's called the ROAMS initiative at Caltech, Robotic Assisted Mobility Science Initiative. And the idea is to develop more and more advanced controllers for exoskeletons and prosthetics using these ideas. So this is now in my lab. These are my graduate students. And Megan, who's wearing the device, is not a paraplegic, thankfully, but she can wear the device and we can test out ideas on this device in the lab at a much faster loop rate than we can in a clinical setting. So I'm going to show a couple examples of that. The first one I really like because it ties together what I talked about earlier, barrier functions. So you saw barrier functions. I presented them to you. But here's the idea. Let's use barrier functions for variable assistance on exoskeletons. So what we're going to do is, so far the results I showed you on the exoskeletons was we generated a stable walking gait for the device. A person got in, used the device. He or she had no impact whatsoever on what the exo was doing. They were literally along for the ride. And I've ridden this exo. It's awesome, but it's also it just forces you to go through, right? So the question is, what if the person doesn't have a complete spinal cord injury, but a partial spinal cord injury or stroke? Can we give them partial assistance, variable assistance, while keeping them safe? And so the idea here is let's take tubes around these nominal trajectories. So the green lines you're seeing are the provably stable trajectories that will result in walking. We take tubes around them. The tubes define your barrier functions. And what we do is by changing this gamma, we can change how aggressively we stay away from the boundary of the tube. That is, we can assist more or less depending on what we want to do. Hence, we can do variable assistance. So this is being tested with different assistance levels in my lab. Megan and Thomas are doing the tests, my graduate students. And the mask you see is measuring metabolic cost. So what we're doing is seeing how much work she's doing relative to the assistance level we're offering. And presumably, if we're doing this right, for full assistance, she should do less work than for partial assistance, right? Because she should start to have to do some of the work. We did this on 8 subjects just to be thorough. And we did this testing, 20 to 30 minutes of metabolic testing. And the end result is we found exactly what we hoped, which was that, in fact, we're doing variable assistance. They have more input into the movement of the system with the barrier functions that they have without them. So that's one application. Another one is to start bringing learning into the mix. So there's 2 ways you can do learning in this context. The first is actually at the control level, kind of like what I talked about with barriers. In this case, we're doing a proof of concept demonstration where we take an RNN and we learn the controller we're applying on the device, and then the RNN does all the control on the device. That is, this device is being 100% controlled by an RNN. So that shows we have the ability to learn these complicated controllers and instantiate them in real time, where the RNN is the one doing the inputs into the system, meaning the RNN's talking to the motors, right? So that's at the low-level control. We can also do learning at the high level. So in this case, think about learning at the decision-making. So in this context, what we're interested in is deciding what gate to actually put on the device. So thus far, what we do is we generate all these gates using the math I showed you. We put them on the device. The person walks with it. That's it. The question is, what gate would the user prefer? So it turns out you can't mathematically figure out what gate is best for a person, or at least maybe you can, but I don't know how to do it, right? The best way to ask what a person likes best is to what? Ask the person, okay? So that leads to preference-based learning. It turns out this is a really powerful way. In essence, what we're doing is learning the cost function of the person by asking them their opinion. And the way you do it is a sort of binary decision process. It turns out we can prove mathematically has really nice properties of convergence to learning this cost. That is, do you like this gate or this gate? Do you like this gate or this gate? And by doing that, just like when you get your glasses checked, right? It's a binary decision, A or B. You can converge in on these optimal costs. You can see the conversion in after multiple trials. And this is what it looks like in action. And what you're going to see now is a bunch of trials where after every trial, the human subject says they like what they would like. And you can see the corresponding sort of cost function you're learning, updating accordingly until we find what the person likes the best. And we can do this both in one direction, meaning changing one variable in the system on the exo, or in multiple directions. So this is an exciting area where we start to bring learning together with dynamics control. The dynamics and control guarantees the properties of the system, and the learning lets you pick what you like best of these properties. So that's the end-to-end conversation. I went through a lot of stuff. I went through a lot of math. I went through a lot of robot videos. But the idea is start with the math. And that's something I obviously firmly believe in. I'm a nonlinear control theorist, so that's bound to be what I say. But hopefully I've convinced you with all the movies that at least there's some merit to doing math, right? So start with the math. We did stability and safety with Lyapunov and barrier. I talked about the extensions of that to autonomy. That there's a whole bunch of work we're doing in my lab on that, and of course all the applications. Remember, the goal in the end was to bridge the gap. The question is, have we bridged the gap? No, we haven't. we're getting better. We're getting much better, but there's a whole bunch of work to do on getting things that work the first time, every time on robotic systems. So we have a lot of work to do in that domain. The one tool I showed you, though, is barrier functions. Remember that Lyapunov is a special case of barrier, so this includes Lyapunov. And this tool, both at the continuous and discrete level, has actually proved really useful to better bridge this gap, and that's the subject of future work, to better understand that connection. The final point I want to make is that I think it's our job as roboticists to think about the real-world applications to what we do and to have an impact in that domain. So there's multiple ways that we're thinking about this, so I want to just, to finish the talk, highlight a couple of these. The first is bringing robots in the public. I think this is a service we can do that's fun for us, and that's demo robots in public settings. And we've done this a lot, and these are just some of my favorite sort of pictures and videos of kids reacting to robots. I just always find these to be awesome. This one was amazing. We were at the DARPA Robotics Challenge finals, and this kid just came up and started dancing with the robot. We see kids, when they see robots walking, start to march with the robots. It's interesting. Even though these robots don't look like people, they definitely feel an emotional connection to them because of their movement. So in some ways, movement is life, right? And so it's great to be able to tap into that connection to get kids excited about, robots and math and engineering and everything else. Of course, there's also applications to real-world settings. I don't have a company. I don't want to start a company. I'm not interested in that domain, but some of my students do. So in this case, one of my former PhD students is the CTO of Miso Robotics, and we work together on hamburger flipping. It turns out that flipping a hamburger is essentially the same as making a robot walk, right? It's surprising but true. And so you have to deal with this friction. It has to be a dynamic maneuver. And so we worked together on this. This was actually deployed in Cali Burger in Pasadena and a couple other Cali Burger locations. So I ate a hamburger cooked by algorithms that my lab came up with, which was really cool. It's also in Dodger Stadium. So the point is, these things do have real-world applications. Of course, the real-world application I'm the most excited about right now is the clinical one. And again, this is only possible because we're working with a company that does clinical testing. I don't have the capability to do that in my lab. But these are images that I didn't show earlier, but these are a bunch of patients testing the exoskeleton and looking at its behavior. And the great thing is we can start to look at what they think about using the device, and we can make decisions based on that. So it's about closing that loop and starting to generate better and better controllers that we ultimately deploy in a clinical setting. So the final thing I want to note out of these videos that's really powerful is that these are clinicians running the device, not engineers. So that's a whole nother level of transition, is when you can have a device that's robust enough to be clinically deployed without engineers necessarily running the device. So again, that's Wondercraft and that's their engineers, but it's great to be part of that collaboration. So with that, the message here is the following. The message is, let's get robots in the real world, and let's get robots working with people to do things that are better. So in this case, this was a video where this is just a student at Caltech. She's not in my lab. She was just sitting on the bench. And we ran Cassie up to her, and she started talking to her. And I thought it was cool, because this is sort of the interaction you'd like to see among these systems. So with that, thank you very much for listening. Yeah. I saw a hand go up here. Yeah, first one I saw. Go for it.
So thank you for a great and very inspiring talk. I have a question on this belief space control barrier function idea. So if I'm not mistaken, the belief dynamics is stochastic dynamics. So what kind of treatments did you have to make to use stochastic dynamics system along with the control barrier function idea?
That's a great idea. So in this case, the discrete time dynamical.
Repeat the question.
Sorry.
Could you repeat the question, please?
The question. So the question was that these belief space dynamics are stochastic in nature. So what modifications do we have to make to the barrier to handle stochastic dynamics? So in this case, we're not handling the stochastic dynamics. We get a discrete time dynamical system that updates the probabilities. So it's not a stochastic barrier per se. That being said, you can also treat things stochastically and deal with stochastic barrier functions. There's been work not in my group, but other groups handling stochastic barriers. So it depends on which perspective you want to take. In our case, this is a discrete time dynamical system updating the probabilities at every given in a discrete time fashion. You can, again, equally view these evolutions sort of stochastically and deal with stochastic barrier functions. And that's a really interesting area to deal with as well. I saw a hand go back there first.
How can you come up with barrier functions for like really complicated systems like walking robots where eventually you only stabilize them over the horizon or over a limit cycle rather than like instantaneously.
Right, right. Great question. So the question was, how do we synthesize barriers? The answer is easily and hardly at the same time. So let me explain a little bit, and this is something I glossed over throughout the whole talk. But I just kind of made it seem like you just pop out a barrier for your set, and then you put it on your system, and the world's a wonderful place, right? It's not that easy in reality. So it turns out that if you have, for example, what I did with the tubes around the trajectories for the exo is much in light with what you had. If you, longer horizons, let's say you have a walking robot, you have a periodic trajectory, you want to keep a barrier function around that trajectory. Or we've also done things like stepping stones. So we have barrier functions for the foot placement of a robot. So you move those barriers around and you can change how the foot is being placed on the robot. So you can synthesize those barriers actually quite easily, because it turns out the barrier function itself defines this set. As a tube, you could look at, making sure the norm distance from your periodic orbit is less than some epsilon, right? So that part's easy. The problem is you don't know if that set that you're defining by H is control invariant. That is, you don't know if there exists an input that will keep you in that set. So the barrier function will tell you the input, but that input might not be feasible. So this process of generating feasible inputs to keep a set invariant is a very, very hard problem that I glossed over here. And we're working on that. We're working on that in a couple contexts. I also should say that a lot of work that's been done in the past feeds into that. For example, if you solve the Hamilton-Jacobi equations, it'll give you a barrier function that is feasible with respect to inputs. Of course, that's not a computationally feasible thing to do. So you do run into this issue that, and I don't want to pretend it's not there, that you have with similarly with Lyapunov functions, in that synthesizing a barrier function that's dynamically feasible, that means at every point in time that QP is generated an input, such that that input can be satisfied by the actuators, is a hard thing, a very hard thing. And there's a whole bunch of PhD topics sitting there for probably the next 10 years because it ties into the fundamental questions about dynamical systems, things like control invariant sets. Okay? Does that answer your question? Okay. I saw another one. Yeah.
I have a question for the exoskeleton prostheses. Are they like absolutely general device that you can use for everyone, or do you have to reprogram it for every specific?
Great question. Great question. So the question was, the exoskeleton stuff I showed, is this general, means anybody gets in this device and walks, or how do you handle it? So I didn't talk about this, but it's actually, I'm glad you asked this because I get to say this now, is that it's not general to every person. And in fact, one of the great things is it doesn't have to be, meaning what we do is, or what Wondercraft does in this case, is because, and they actually build upon Frost, that framework I talked about earlier. So they took Frost, that package, and modified it to run really well in this context. What they do is, and I've written in the EXO, is you measure a patient, okay, a couple key measurements. From there, you can look at biological textbooks and get an estimate of their mass inertia distributions. You create a model of the patient, you intersect that with the model of the EXO. You use that joint model to generate a stable walking gait that's patient-specific. That process takes a couple minutes, 5 minutes maybe. Then from those gaits, they can generate like 10, 20 gaits. They try out a couple, see which one the patient likes best. So it is patient-specific and customizable to a given patient based on that process, right? Great question. Yeah?
Does that process allow for time-varying preferences for the patient?
So right now, no. That's a great question, though. So right now, it actually doesn't even really allow for, it allows for preferences only at a macro level, at a gate level, and a couple binary choices. So what's being implemented clinically right now is they generate a collection of gates, they put them on the EXO, the patient wears it, tries one, they kind of give some high-level feedback to the clinician, they pick another gate, and then that's 2 or 3 gates, and that's it. You're stuck with what you got, right? So what we're doing with the preference-based learning was in some ways trying to mathematically quantify that process and actually generate gates that are really nice. But what we did was not time-based, it was purely gate-based at this moment. The question is, could there be a time-based component, right? Meaning, can you, rather than saying, I want a whole new gate, the patient should be able to say, I want my knee to go a little higher throughout the gait, or I want to take a little bit longer step. Well, that's sort of a gate level, but you see what I'm saying? And that would be awesome to add these sort of modifications around gates in a much more time-sensitive fashion. It's a great area. We've not touched that yet, but that would be really interesting to study. Yeah?
The question. How often only one device will react to conflicting barrier? For example, like if you say a robot to not go too close to a wall, but someone tries to push it to the wall,
Yeah.
how they will react?
Yeah. So the question was, how does the device react to conflicting barrier functions? So this goes back to the earlier point, which is barrier synthesis. So if you have a single barrier function, if it's dynamically feasible, meaning it's defines a control invariant set, you're good to go. Meaning if you start in that, there's no way you're going to hit the wall because you verified ahead of time that you can't hit the wall, and the barrier function enforces that. If you have multiple barriers, I talked earlier about intersection and union. Turns out this gets much more difficult. You can't just, the easier way would be just add a bunch of constraints in your QP with all your barriers. But you might go infeasible then. It might not be possible to satisfy all at the same time, right? So in that case, you have to get smart, either with the synthesis, by intersecting or unioning to make sure it becomes sort of min-max problem. There's a whole bunch of stuff in that light that you have to take into account. So yes, that's a real problem that requires careful study. There's been study done on this. Jorge Cortez and Magnus did a nice paper on doing min-max operations for intersection and union on continuous time barriers. I talked about min-max on discrete time barriers a little bit. So there's a whole wealth of things to do to try to answer this problem. But yeah, I don't want to imply that you just define a bunch of barriers, throw them together on your hardware, it's safe, you're done, right? Life's never that easy. Yeah. I see one in the back.
The people in the video seem to be swinging their upper bodies a little more than usual.
Yeah. In the exoskeleton videos?
Yeah.
Good question. So in the exoskeleton videos, the question was the people seem to be swinging their arms a little more than usual. That is true in the sense that these were paraplegics with injuries from the waist down, so they have an upper body torso, and they are helping to stabilize the device. Now, the reason we showed the video with the exo walking without a patient in it was to prove that, in fact, the device can walk on its own. But that being said, the human will help to stabilize it further. And right now, the device itself and the walking, while stable, could be stabilized further, made more robust. And that's something we're working on the control side, right? So the human's helping with that through their dynamics. But that's what you're seeing is they don't feel that the gait is as stable as they'd like it, so they swing their arms to stabilize further.
All right. And I think that we're done, so let's thank